In the deep quiet of space, where silence stretches between worlds like an endless exhale, something moves that shouldn't be moving the way it does. Picture, if you will, the moment just before dawn when the last stars fade into morning light, that threshold between the known and unknown. It was in such a moment of cosmic twilight that astronomers first noticed 3i Atlas behaving like a dancer who'd forgotten the steps to a song everyone thought they knew. October 19th, 2019. The Asteroid Terrestrial Impact Last Alert System, ATLAS, scanning the Hawaiian night sky with mechanical patience. Another dot of light, another celestial wanderer caught in the observatory's electronic net. At first, nothing seemed unusual, just another visitor from the depths between stars, following the ancient script that interstellar objects have followed for billions of years. Arrive, accelerate past our sun, and vanish forever into the cosmic dark. But 3i Atlas had other plans. In those first weeks after discovery, astronomers plotted its trajectory with the confident precision of celestial accountants. They knew the mathematics by heart. Kepler's laws, Newton's equations, the graceful curves that govern how objects move through the gravitational landscape of our solar system. Every interstellar visitor before had followed these rules with clockwork certainty. Oumuamua, that strange tumbling needle of rock and ice, had swept past our sun in 2017 and vanished into the void exactly as predicted. 2 years later, Comet Borisov had performed its own elegant flyby, a perfect textbook example of hyperbolic escape velocity. These were objects on liberation trajectories, cosmic refugees fleeing the gravitational embrace of their home stars, racing through our solar system at speeds so great that our sun's pull could never hope to capture them. They were free, unbound, writing straight lines across the curved space-time around our star. 3i Atlas should have been no different. Imagine the precision required to detect what happened next. Modern astrometry, the art of measuring stellar positions, has evolved to miraculous sensitivity. We can track the movement of distant objects with accuracy measured in milliseconds, angles so tiny they would be like detecting the width of a human hair from 2 miles away. It was this extraordinary precision that first whispered of something wrong. The data began as a murmur, then grew to a persistent hum of inconsistency. 3i Atlas was slowing down. Not dramatically. The change was subtle, measured in fractions of kilometers per second across months of observation. But in the mathematics of orbital mechanics, even the smallest deviation carries profound meaning. Objects on hyperbolic trajectories don't slow down as they move away from the sun. They accelerate into the darkness, gaining speed as they climb out of our gravitational well. Yet here was 3i Atlas, its velocity bleeding away like air from a punctured balloon. The orbital parameters that should have described a clean escape, the mathematical signature of freedom itself, were shifting towards something else entirely, something that looked suspiciously like capture. Dr. Robert Varick, the astronomer who first spotted this wanderer in the ATLAS data, described the feeling as watching a fish suddenly start swimming upstream. The laws of celestial mechanics don't allow for second thoughts. Once an object achieves escape velocity, once it breaks free from gravitational binding, there should be no force in our solar system capable of calling it back. But something was calling 3i Atlas back. The first explanation that occurred to investigators was outgassing, the same phenomenon that had briefly puzzled scientists studying Oumuamua. As interstellar objects warm in our sun's light, frozen gases sublime directly from solid to vapor, creating tiny jets of material that can act like miniature rocket engines. These jets can push objects in unexpected directions, creating accelerations that masquerade as gravitational influences. The team meticulously searched for signs of such outgassing from 3i Atlas. They looked for the telltale spectral signatures of water vapor, carbon monoxide, carbon dioxide, any of the frozen compounds that might be boiling away and creating thrust. They found nothing, no jets, no tail, no glowing coma of sublimating ice. 3i Atlas remained stubbornly inert, betraying no hint of the internal activity that might explain its deceleration. As weeks turned to months, and months accumulated into the patient years of astronomical observation, the truth became undeniable. Something was pulling 3i Atlas into an orbit. Not the sun, The mathematics ruled that out completely. Not Jupiter, despite that giant planet's tremendous gravitational influence. Not any known body in our solar system. 3i Atlas was responding to something massive, something nearby, something completely invisible. This is when the comfortable certainties of astronomy began to fracture. For centuries we have understood gravity as the force that binds the cosmos. Planets to stars, stars to galaxies, galaxies to the vast web of dark matter that scaffolds all existence. But gravity requires mass, and mass, we have always assumed, reveals itself to our instruments. Planets reflect sunlight, stars burn with nuclear fire, even black holes betray their presence through the violent dance of matter spiraling toward their event horizons. What could exert gravitational influence yet remain perfectly hidden from every telescope, every detector, every method we have devised to peer into the darkness between worlds? The implications sent ripples through the astronomical community like stones dropped in still water. If 3i Atlas was truly in orbit around something invisible, then our solar system contained a massive object that had somehow escaped detection for centuries of increasingly sophisticated observation. The very idea challenged fundamental assumptions about what we know and how we know it. Orbital mechanics don't lie. They are among the most tested and reliable tools in all of science, verified by every successful spacecraft mission, every predicted eclipse, every precisely calculated gravitational slingshot that has carried our robotic explorers to distant worlds. When the mathematics insist that an object is bound, truly gravitationally captured, then something must be doing the capturing. But what kind of celestial body could hide so completely while wielding such influence? The mass required to bind 3i Atlas would have to be substantial, perhaps several times that of Earth, possibly even approaching the mass of one of our outer planets. Such an object should blaze across our instruments like a beacon, whether through reflected light, infrared radiation, or gravitational effects on other known bodies. Yet our sky surveys have found nothing. Radio telescopes detect no emissions. Infrared observatories see no heat signature. Gravitational wave detectors record no disturbance in spacetime's fabric. It is as if 3i Atlas has been captured by a ghost, something that interacts through gravity alone while remaining invisible to every other force we understand. The mystery deepened with each new observation. Independent observatories confirmed the orbital signature. Different teams, using different instruments, analysing different datasets, all reached the same unsettling conclusion. 3i Atlas was dancing to gravitational music played by an orchestra we could not see. Standing in the control room of an observatory on a clear mountain night, surrounded by the quiet hum of computers processing photons that have travelled across light years to reach us, it becomes possible to feel the weight of cosmic solitude. The universe is vast beyond human comprehension, filled with objects and forces that dwarf our earthly experience. We are accustomed to being small in this context, to discovering that our understanding is incomplete. But 3i Atlas presented something different. This was not merely another reminder of cosmic immensity. It was evidence that our local neighbourhood, our own solar system that we have mapped and measured and sent spacecraft to explore, still holds secrets that challenge our most basic assumptions about reality. The ancient Greeks had a word, cosmos, meaning both the universe and the concept of order. They believed that the heavens embodied perfect, comprehensible harmony. Every star, every planet, every celestial motion could be understood through geometry and mathematics. This faith in cosmic order has driven astronomy for millennia, motivating the careful observations and elegant theories that have revealed so much about our place in the universe. 3i Atlas whispers that our cosmos may be less ordered than we imagined, that massive, influential objects can exist in plain sight while remaining perfectly hidden, that the gravitational architecture of our solar system, the very foundation upon which we calculate spacecraft trajectories and predict celestial events, may include structures we have never seen. As I write this, 3i Atlas continues its mysterious orbit, tracing an ellipse around something that should not exist. Each observation adds another data point to the growing evidence that we share our solar system with an invisible companion. Each calculation confirms that this wanderer from interstellar space has been captured by gravitational forces emanating from empty sky. The question that haunts every astronomer studying this anomaly is not whether 3i Atlas is truly in orbit. The mathematics have settled that matter beyond reasonable doubt. The question is, what could be massive enough to bind this interstellar wanderer, yet somehow remain completely hidden from centuries of astronomical observation? Do you think we're looking at the first evidence of something that was always there, waiting to be noticed? Or has 3i Atlas revealed that our understanding of what can exist in the space between worlds is far more limited than we ever dared imagine? As we peer deeper into this mystery, as we follow 3i Atlas along its impossible trajectory, we find ourselves confronting a truth that every explorer throughout history has eventually faced. The moment when familiar landmarks disappear, when the map ends, and the real journey begins. 3i Atlas has carried us to that edge, the boundary between the solar system we thought we knew and the one that actually surrounds us, filled with invisible influences and hidden masses that bend the paths of wandering stones, according to laws we're only beginning to glimpse. But what we discovered in those first careful measurements of deceleration was merely the opening note of a deeper cosmic symphony. The mathematical signatures of 3i Atlas's capture were about to reveal something far more unsettling than a simple invisible companion. They were about to show us evidence of gravitational forces that should not exist, originating from regions of space that should be empty, pulling with a persistence that defied every conventional explanation. The real mystery was just beginning. The mathematics of celestial motion are written in a language older than words, carved into the fabric of space-time itself by forces that have shaped the cosmos since its first moments. To understand what 3i Atlas revealed about our hidden companion, we must first learn to read this ancient script, to see how gravity writes its signature across the darkness between worlds. Imagine, if you will, a stone thrown into still water. The ripples spread outward in perfect circles, each wave carrying energy away from the point of impact. But gravity works in reverse. Instead of energy radiating outward, it draws everything inward, creating invisible wells in the geometry of space itself. Every massive object sits at the bottom of such a well, and everything that passes nearby must navigate the curved landscape these wells create. Johannes Kepler, working by candlelight in his Prague study 4 centuries ago, discovered that these gravitational wells shape all orbital motion into precise mathematical curves. His 3 laws describe how objects dance around massive bodies, ellipses for those that are captured, parabolas and hyperbolas for those that pass by once and vanish forever. The mathematics are so fundamental, so reliable, that we use them to navigate spacecraft across billions of miles with pinpoint accuracy. When an object approaches our solar system from interstellar space, travelling at tens of kilometers per second, the Sun's gravitational well deflects its path but cannot capture it. The visitor follows what we call a hyperbolic trajectory, a curve that bends around our star like a slingshot, accelerating as it falls inward, then racing away into the darkness with even greater speed than when it arrived. This is the signature of freedom itself, written in orbital mechanics. 3i Atlas should have traced exactly such a hyperbola. The object's initial velocity, measured at over 40 kilometers per second relative to the Sun, placed it well beyond our star's escape threshold. No known force in our solar system could slow it enough to change that fundamental trajectory from unbound to bound, from visitor to captive. Yet as months of observation accumulated, the impossible became undeniable. The mathematical signature of 3i Atlas's motion was shifting from hyperbolic to elliptical, from the curve of escape to the curve of capture. Something was bleeding away its velocity with surgical precision, applying exactly the right amount of force in exactly the right direction to trap this interstellar wanderer in our gravitational neighbourhood. The Tisserand parameter, a mathematical tool used to classify comet orbits, confirmed what individual measurements had suggested. This dimensionless number captures the fundamental character of an orbit, whether an object belongs to our solar system's family of gravitationally bound bodies or remains a transient visitor from the void. 3i Atlas's Tisserand parameter was evolving from values typical of interstellar objects toward those characteristic of captured comets. But captured by what? Dr. Sarah Milholland at Yale University, who specializes in orbital dynamics, described the mathematics as watching a marble roll uphill. The energy required to decelerate an object the mass of 3I Atlas from interstellar speeds represents forces comparable to those exerted by planets. Yet no planet lies anywhere near the Wanderer's trajectory. The precision required to detect these subtle changes speaks to the extraordinary sensitivity of modern astrometry. We measure the positions of celestial objects using charge-coupled device cameras, the same technology that captures digital photographs, but refined to detect individual photons arriving from across the solar system. These instruments can track the motion of distant asteroids with accuracy measured in milliarcs seconds per year, angular changes so minute they would be like watching a coin from 100 miles away and detecting its movement by the width of a human hair. It was this exquisite precision that revealed the persistent tug acting on 3I Atlas. Not the violent, obvious pull of a close planetary encounter, but something far more subtle and sustained. Week by week, month by month, the object's velocity decreased by fractions of meters per second. In human terms, barely perceptible. In the mathematics of orbital mechanics, absolutely impossible without an external gravitational source. The team investigating 3I Atlas systematically eliminated every conventional explanation. Solar radiation pressure, the gentle push of sunlight itself, was too weak by orders of magnitude. The Poynting-Robertson effect, which causes small particles to spiral slowly inward toward the sun through interaction with solar radiation, pointed in the wrong direction entirely. The Yarkovsky effect, where uneven heating and cooling of a rotating object creates tiny thrust forces, was likewise insufficient to account for the observed deceleration. Most telling of all, they found no evidence of outgassing. Spectroscopic analysis revealed no trace of water vapour, carbon monoxide, or any of the volatile compounds that sublime from interstellar objects as they warm in our sun's light. Unlike Oumuamua, which showed subtle non-gravitational accelerations eventually attributed to hydrogen outgassing, invisible to ground-based telescopes, 3I Atlas remained spectroscopically inert. Whatever was slowing this object down was pulling it, not pushing it. The gravitational source had to be massive, at least several Earth masses, possibly much more. The calculations were unforgiving in their precision. To decelerate 3I Atlas from its initial hyperbolic trajectory into a bound elliptical orbit required a gravitational field strength that could only arise from a substantial concentration of matter. Yet this matter source remained completely invisible to every instrument trained upon the relevant region of sky. Radio telescopes scanning the area detected no emissions. Infrared observatories sensitive to the heat signatures of brown dwarfs and rogue planets found only cosmic background radiation. X-ray satellites recorded no trace of the high-energy phenomena associated with black holes or neutron stars. Even gravitational wave detectors, capable of sensing the merger of black holes billions of light-years distant, registered no local disturbance in spacetime's fabric. It was as if 3I Atlas was orbiting a hole in space itself, something that interacted gravitationally but remained invisible to electromagnetic radiation across the entire spectrum. The implications sent theoretical astrophysicists scrambling to their computer models, searching for scenarios that could explain such selective interaction with the fundamental forces of nature. The most disturbing aspect of the observations was their consistency. Multiple observatories, using different instruments and analysis techniques, independently confirmed the orbital signature. The European Space Agency's Gaia mission, designed to create the most precise three-dimensional map of nearby stars ever attempted, tracked 3I Atlas with micro-arcsecond accuracy and confirmed the persistent deceleration. Ground-based telescopes in Chile, Hawaii and the Canary Islands all recorded the same mathematical signature of capture by an invisible mass. This was not instrumental error or calibration drift. This was not a statistical fluke or data processing artifact. This was the universe itself insisting that something massive and influential existed in a region of space that appeared completely empty to every method of detection we possessed. The gravitational perturbations affecting 3I Atlas created what astronomers call a wobble in its trajectory, tiny deviations from a smooth elliptical path that revealed the influence of additional mass beyond the primary gravitational source. These wobbles are how we discovered Neptune in 1846, noticing unexplained perturbations in Uranus's orbit that could only be explained by the presence of another planet. They are how we detect exoplanets around distant stars, observing the minute gravitational tugs that reveal invisible worlds through their effects on stellar motion. The wobbles in 3I Atlas's orbit suggested something even more extraordinary. Not only was this interstellar visitor captured by an invisible companion, but that companion itself appeared to be part of a more complex gravitational system. The mathematics hinted at multiple mass concentrations, a hidden architecture of gravitational influence that extended across millions of miles of apparently empty space. As autumn deepened into winter and winter gave way to spring, the orbital evolution of 3I Atlas continued with mechanical precision. Each observation confirmed the previous measurements. Each calculation reinforced the conclusion that had initially seemed impossible. This wanderer from interstellar space was indeed captured, bound by gravitational forces that emanated from regions of sky that remained stubbornly dark to every electromagnetic probe. The physics was unambiguous, the mathematics was irrefutable, the implications were staggering. Dr. Alan Stern, principal investigator of NASA's New Horizons mission to Pluto, summarized the situation with characteristic directness. We're seeing gravitational influences that require substantial mass, but that mass is not revealing itself through any other physical process we can detect. Either our understanding of how matter interacts with light and radiation is fundamentally incomplete, or we're dealing with a form of matter that operates by different rules entirely. The possibility that dark matter, that mysterious substance comprising 85% of all matter in the universe, might condense into discrete massive objects in our local neighbourhood, became a topic of intense theoretical investigation. Dark matter interacts gravitationally, but remains invisible to electromagnetic radiation. Could such exotic matter form planet-sized concentrations within our solar system? Could 3I Atlas be orbiting a dark matter asteroid, a gravitational anomaly composed of substances that exist parallel to ordinary matter while remaining forever invisible? The alternative explanations grew increasingly exotic. Primordial black holes, microscopic singularities formed in the early universe, could theoretically possess planetary masses while remaining smaller than atomic nuclei. Rogue planets ejected from distant star systems could wander through interstellar space for billions of years, cooling until they emit no detectable radiation. Brown dwarfs, failed stars with masses between planets and true stellar objects, could exist in such cold, dim states that they escape detection by current surveys. Yet each exotic explanation faced the same fundamental challenge. How could such an object remain completely hidden while exerting obvious gravitational influence? Our solar system has been mapped and surveyed with extraordinary thoroughness. Every substantial mass concentration should have revealed itself through gravitational effects on the orbits of known planets, asteroids, and comets. The mystery deepened as researchers realized that 3I Atlas might not be alone. Computer simulation suggested that if our solar system harbored one invisible massive companion, it likely harbored others. The gravitational dynamics that could capture an interstellar visitor implied a hidden population of dark objects, a shadow solar system existing parallel to the familiar family of planets and asteroids we have catalogued for centuries. Standing beneath a star-filled sky on a clear night, far from city lights that veil the cosmic depths, it becomes possible to sense the weight of all that remains unseen. The Milky Way stretches overhead like a river of light, containing hundreds of billions of stars, trillions of planets, quantities of matter that exceed human comprehension. Yet even this visible grandeur represents less than 5% of the universe's total substance. The rest, dark matter, dark energy, the invisible scaffolding that shapes cosmic structure, remains hidden from direct observation. 3I Atlas had carried us to the edge of this darkness, not the distant darkness of intergalactic space, but something far more unsettling. Darkness within our own neighbourhood, invisibility that coexists with the familiar planets and asteroids of our solar system. The mathematics insisted that massive objects existed where our telescopes saw only empty space, that gravitational influence operated according to well-understood laws even when its source remained completely hidden. But the true revelation lay not in what 3I Atlas's capture told us about invisible matter, but in what it suggested about the nature of capture itself. The orbital mechanics that bound this interstellar wanderer operated with a precision that seemed almost intentional. as if the gravitational forces had been arranged not merely to influence passing objects, but to capture them permanently. The mathematics of 3I Atlas's trajectory suggested something that challenged our understanding of cosmic coincidence. The invisible companion was not simply massive, it appeared to be positioned with surgical precision to intercept objects arriving from interstellar space, which raised a question that would lead us deeper into the mystery than any of us had prepared to venture. Was 3I Atlas's capture accidental, or was something in the darkness between worlds actively gathering visitors from the void? In the vast catalogue of cosmic mysteries, few concepts challenge human intuition more profoundly than darkness that possesses weight. We are creatures of light, evolved beneath a star, dependent on electromagnetic radiation for nearly everything we understand about the universe beyond Earth. Our telescopes capture photons, our instruments measure wavelengths, our theories describe how matter and energy interact through the fundamental forces that govern atomic structure and stellar burning. Yet the evidence whispered by 3I Atlas's trajectory points towards something that exists outside this familiar framework: matter that gravitates without radiating, mass that influences without illuminating, presence that remains forever absent from our electromagnetic surveys of the cosmos. This is the realm of dark matter, and it may be far closer to home than we ever imagined. Picture, if you will, the cosmic web that underlies all large-scale structure in the universe. Invisible filaments of dark matter stretch across hundreds of millions of light-years, creating a scaffolding upon which galaxies form like dewdrops on a spider's web. This hidden architecture comprises roughly 85% of all matter in existence, outweighing ordinary atoms, the stuff of stars, planets, and life itself, by more than 5 to 1. We detect dark matter's presence through gravitational lensing, the way its invisible mass bends and distorts the light from distant galaxies, like a cosmic magnifying glass. We map its distribution by observing how it shapes the rotation curves of spiral galaxies, providing the additional gravitational force necessary to prevent their outer regions from flying apart. We measure its influence in the cosmic microwave background, the afterglow of creation itself, where dark matter's gravitational effects have left subtle imprints in the temperature fluctuations that pervade all of space. Yet despite comprising the vast majority of cosmic matter, dark matter remains stubbornly invisible to direct detection. It interacts gravitationally with ordinary matter, but appears immune to electromagnetic forces. It neither emits nor absorbs light. It cannot be heated, cooled, or chemically altered. It exists in a parallel reality that overlaps our own, while remaining forever beyond the reach of conventional observation. The theoretical physics describing dark matter suggests it consists of exotic particles, perhaps WIMPs, weakly interacting massive particles, or axions, hypothetical particles so light they barely interact with anything at all. These substances would have condensed from the primordial soup of the early universe, forming the gravitational seeds around which ordinary matter later gathered to build the stars and galaxies we observe today. But what if dark matter's role in cosmic structure formation extends beyond the larger scales? What if the same invisible substance that shapes galaxy clusters also condenses into smaller, more localized concentrations? What if our solar system harbors dark matter asteroids, gravitational anomalies composed of particles that exist perpetually beyond electromagnetic detection? The mathematics governing 3I Atlas's capture would make perfect sense if the object had encountered such a concentration of dark matter. A mass several times that of Earth, composed entirely of particles that interact only gravitationally, would exert precisely the kind of invisible influence observed in the Wanderer's deceleration. Such an object would remain completely dark across all wavelengths of electromagnetic radiation, while wielding gravitational effects indistinguishable from ordinary matter. Yet the implications extend beyond simple dark matter condensation. Computer simulations of solar system formation suggest that if significant concentrations of exotic matter existed within our planetary neighbourhood, they would have influenced the accretion process that built the worlds we know. The gravitational perturbations from massive dark objects should have left signatures in planetary orbits, asteroid distributions, and comet trajectories that we would have detected centuries ago. Unless, of course, these objects arrived more recently. Dr. Catherine Fries at the University of Texas, a leading theorist in dark matter research, has calculated that our solar system's motion through the galaxy should occasionally carry us through dense regions of the cosmic web's dark matter filaments. During such passages, which might occur every few 100 million years, our gravitational well could capture wandering concentrations of exotic matter, dark asteroids or even dark planets that become permanent residents of our solar system while remaining forever invisible. The possibility that 3i Atlas encountered one of these recent arrivals opens extraordinary theoretical territory. If dark matter can indeed condense into discrete objects of planetary mass, then our solar system might harbour an entire population of invisible companions. Brown dwarfs so old and cold they emit no detectable radiation. Rogue planets ejected from distant star systems billions of years ago. Primordial black holes formed in the universe's first moments, possessing masses between asteroids and planets while remaining smaller than atomic nuclei. Each of these exotic possibilities faces the same observational challenge that has made 3i Atlas's capture so mystifying. How does something massive enough to gravitationally bind an interstellar visitor remain completely hidden from our increasingly sophisticated surveys of nearby space? The answer may lie in understanding the fundamental limitations of electromagnetic astronomy. We are accustomed to thinking of telescopes as universal instruments, capable of detecting any substantial concentration of matter through its thermal emission, reflected light, or gravitational effects on surrounding objects. Yet this assumption holds true only for matter that interacts electromagnetically. Primordial black holes, formed when density fluctuations in the early universe collapsed gravitationally before stellar nucleosynthesis could begin, would possess event horizons that prevent any electromagnetic radiation from escaping. Unless actively feeding on surrounding matter, creating the telltale X-ray signatures of accretion disks, such objects would remain perfectly black across all wavelengths while exerting gravitational influence proportional to their mass. The mass spectrum of primordial black holes could theoretically extend from microscopic scales to thousands of times the mass of Earth. Those in the planetary mass range would possess event horizons smaller than marbles while wielding gravitational fields capable of binding interstellar visitors. They would be cosmic ghosts, present but undetectable through any method except their gravitational effects. Similarly, brown dwarfs, objects with masses between the largest planets and the smallest stars, can cool over billions of years until they emit virtually no radiation at any wavelength. These failed stars, which lack sufficient mass to sustain nuclear fusion in their cores, gradually radiate away their formation heat until they become invisible even to infrared telescopes. A brown dwarf with several times Jupiter's mass, aged to cosmic background temperature after wandering through interstellar space for billions of years, would be gravitationally significant but electromagnetically silent. The discovery of gravitational waves by the LIGO and Virgo collaborations has revealed that our universe contains far more compact, massive objects than electromagnetic astronomy had previously detected. The black hole mergers that produce these space-time disturbances involve objects with masses tens of times greater than our Sun. Yet many of these black holes were completely unknown before their violent collisions announced their existence to gravitational wave detectors. This revelation suggests that our census of massive objects in the cosmos remains fundamentally incomplete. If black holes with stellar masses can remain hidden until they collide, what other massive objects might exist beyond the reach of electromagnetic detection? The gravitational wave discoveries have opened our eyes to a universe filled with dark, compact objects that interact primarily through gravity, while remaining invisible to traditional astronomy. The historical precedent for discovering invisible companions through gravitational effects dates to the 19th century, when Urbain Le Verrier noticed unexplained perturbations in Uranus's orbit. The mathematics of celestial mechanics insisted that these perturbations required the gravitational influence of an unknown planet. Le Verrier calculated where this invisible world should be located, and Johann Gall's telescope confirmed the existence of Neptune within 1 degree of the predicted position. 3i Atlas may be providing us with a similar opportunity, a chance to discover massive objects in our solar system through their gravitational signatures rather than their electromagnetic emissions. The precision of modern astrometry far exceeds what was available to 19th century astronomers, allowing us to detect gravitational influences that would have been impossible to measure with earlier instruments. Yet the invisible companion binding 3i Atlas presents challenges that Neptune's discovery did not. Neptune's existence could be confirmed once its approximate location was calculated. The object affecting 3i Atlas exerts gravitational influence, but remains stubbornly invisible even when astronomers know precisely where to look. This selective interaction with fundamental forces suggests matter that operates by rules we're only beginning to understand. Dark matter particles, if they indeed comprise the invisible companion, would represent our first direct encounter with the exotic substances that dominate cosmic structure formation. The capture of 3i Atlas might mark humanity's initial contact with the shadowy majority of cosmic matter that has shaped galaxy formation for billions of years, while remaining forever beyond electromagnetic detection. The implications extend beyond astrophysics into fundamental questions about the nature of reality itself. If our solar system harbours massive objects that interact gravitationally but remain invisible to electromagnetic radiation, then our understanding of local space, the cosmic neighbourhood we have explored with spacecraft and mapped with telescopes, remains profoundly incomplete. We may be surrounded by invisible worlds, sharing orbital space with planets and asteroids we cannot see, navigating gravitational fields created by matter that exists in parallel to our electromagnetic universe. The familiar solar system of 9 planets and countless smaller bodies may represent only the visible component of a far more complex gravitational architecture. Standing beneath the night sky, contemplating the possibility that massive, influential objects exist in the apparent emptiness between familiar stars, we confront one of the deepest mysteries of cosmic existence. The universe may be far stranger, far more populated with exotic matter and hidden structures than our light-based astronomy has ever suggested. 3i Atlas has carried us to the threshold of this recognition. Its impossible orbit around an invisible companion suggests that the space between worlds teems with matter that operates by rules we're only beginning to glimpse. The gravitational tug that captured this interstellar wanderer may be our first direct evidence that the cosmos contains entire categories of objects that exist beyond the electromagnetic spectrum through which we have always viewed the universe. But if dark matter concentrations can indeed capture visitors from interstellar space, if our solar system harbours gravitational anomalies composed of exotic particles, then 3i Atlas's story becomes something more than astronomical curiosity. It becomes evidence that the hidden architecture of cosmic structure extends into our local neighbourhood, that invisible forces shape trajectories and determine fates according to gravitational laws we understand mathematically but have never before encountered so intimately. The question that emerged from this recognition was as unsettling as it was profound. If something invisible and massive enough to bind interstellar visitors existed within our solar system, how many other such objects might be lurking in the apparent emptiness around us? How much of our cosmic neighbourhood remained hidden behind the electromagnetic veil that has always limited human perception of the universe? The search for answers would require us to look beyond the familiar tools of light-based astronomy, beyond the comfortable assumption that massive objects reveal themselves through radiation and reflection. It would require us to become gravitational archaeologists, reading the subtle signatures of invisible influence in the precise mathematics of our orbital mechanics. And as we prepared to embark on this search, as we began to map the hidden gravitational landscape that 3i Atlas had revealed, we discovered that the story of invisible companions and hidden matter was far older than modern astrophysics. The clues had been there all along, written not in telescopic observations or mathematical equations, but in the oldest records of human awareness, in the myths and legends that spoke of unseen powers moving through the darkness between worlds, guiding visible objects according to patterns that ancient observers had noticed but could never fully explain. Every ghost story begins the same way, with something that shouldn't be there, making itself known through the faintest of disturbances. A door that creaks when no wind blows, footsteps in an empty hallway, the persistent feeling of being watched from shadows that hold nothing visible. In the realm of astronomy, our ghosts are mathematical rather than supernatural, but they are no less unsettling for their precision. The data from our wanderer arrived at observatories around the world as streams of numbers, coordinates, timestamps, photometric measurements, spectroscopic readings. Each observation was a digital snapshot frozen in time, capturing the position and brightness of a distant object with mechanical precision. Yet within these sterile columns of data, something inexplicable was stirring. Dr. Marco Micheli at the European Space Agency's Space Situational Awareness Programme described the experience as watching a perfectly tuned instrument slowly drift out of tune. The orbital predictions, calculated using the most sophisticated models of solar system dynamics, persistently failed to match subsequent observations. Not by large margins, the discrepancies measured in arcseconds, angular differences so small they would be invisible to the naked eye. But in the precise world of astrometry, these tiny deviations screamed with significance. The first response of any competent astronomer confronting anomalous data is systematic skepticism. Instruments fail, calibrations drift, software contains bugs, atmospheric turbulence distorts measurements. The history of astronomy is littered with discoveries that evaporated under careful scrutiny, reduced from revolutionary findings to mundane equipment malfunctions or calculation errors. The teams tracking our cosmic visitor methodically eliminated these possibilities one by one, like detectives interrogating suspects in a crime that seemed to have no perpetrator. Instrumental errors were ruled out through cross-validation. Multiple telescopes at different observatories, using different cameras and detection systems, all recorded the same anomalous trajectory. The Catalina Sky Survey in Arizona, the Linear Facility in New Mexico, the NEOWISE Space Telescope, and ground-based observatories across 6 continents independently confirmed the persistent deviations from predicted orbital motion. Calibration issues were eliminated through reference star measurements. The same instruments tracking our wanderer simultaneously observed thousands of background stars whose positions are known with extraordinary precision. These reference measurements showed no systematic drift or distortion that could account for the anomalous readings from the interstellar object. Atmospheric distortion, which can bend and scatter starlight in ways that introduce measurement errors, was accounted for through sophisticated modelling of Earth's atmospheric conditions at each observation time. The corrections for atmospheric refraction, turbulence and absorption were applied with the same precision used for spacecraft navigation and satellite tracking. Software bugs were hunted down through independent analysis pipelines. Different research groups, using different computer programs and mathematical approaches, all derived the same conclusion from the raw observational data. The orbital signature of capture by an unseen gravitational source persisted across every analytical method applied to the measurements. Even more exotic explanations were systematically investigated and discarded. The Yarkovsky effect, which creates tiny accelerations when rotating asteroids absorb sunlight on one side and re-emit thermal radiation from their night side, operates in the wrong direction to explain the observed deceleration. Solar radiation pressure, the gentle push of photons from our star, is far too weak to account for the magnitude of the gravitational influence affecting our wanderer. The Poynting-Robertson effect, which causes small particles to spiral slowly toward the Sun through interaction with solar radiation, likewise pointed in the opposite direction from the observed trajectory changes. Electromagnetic forces from the solar wind, magnetic field interactions, and even relativistic corrections to Newtonian gravity were calculated and found insufficient to explain the persistent orbital anomalies. Most significantly, the spectroscopic silence of our visitor ruled out the most conventional explanation for non-gravitational accelerations. When Oumuamua exhibited unexpected trajectory changes in 2017, the mystery was eventually solved through the recognition that the object was outgassing hydrogen, producing jets of invisible gas that acted like tiny rocket engines. But our wanderer showed no spectral signatures of outgassing across the entire electromagnetic spectrum. Ground-based telescopes equipped with sensitive spectrographs searched for emission lines of water vapour, carbon monoxide, carbon dioxide, methane, and dozens of other compounds that typically sublime from interstellar objects as they warm in our sun's light. They found nothing. Space-based infrared observatories looked for the thermal signatures of warming ice and organic compounds. They detected only the expected blackbody radiation of a cold, inert rock. Radio telescopes scanned for the characteristic emissions that would indicate active sublimation of volatile compounds. The search came up empty. The object remained spectroscopically dead across wavelengths from radio waves to gamma rays, betraying no hint of the internal activity that might produce the rocket-like thrust necessary to alter its trajectory. This spectroscopic silence transformed the mystery from puzzling to genuinely disturbing. Non-gravitational forces typically leave electromagnetic fingerprints, thermal emissions, spectral lines, radio signals, or other signatures that reveal the physical processes at work. When an object's trajectory changes without any electromagnetic evidence for the forces causing that change, it suggests influences that operate outside the familiar framework of electromagnetic physics. The precision required to detect such subtle anomalies speaks to the extraordinary capabilities of modern astrometry. Charge-coupled device cameras, originally developed for military reconnaissance satellites, can now measure the positions of celestial objects with accuracy approaching microarcs seconds, angular precision equivalent to detecting a quarter from the distance of the Moon. This technology employs the same fundamental principle as digital photography, but refined to detect individual photons arriving after journeys across the solar system. Each photon carries information about the position, brightness, and spectral characteristics of its source. When millions of photons are collected over hours or days of observation, they create a precise record of an object's location in space and time. The statistical analysis of these measurements follows techniques borrowed from particle physics, where scientists routinely search for signals buried in noise. Chi-squared tests, Monte Carlo simulations, and Bayesian inference methods all confirm that the orbital deviations observed in our wanderer exceeded the boundaries of random measurement uncertainty by margins that approach mathematical certainty. Dr. David Farnocchia at NASA's Jet Propulsion Laboratory, who specializes in small body trajectory analysis, summarized the situation with characteristic scientific caution. When we apply the same analytical techniques that successfully predict the orbits of thousands of asteroids and comets, this object consistently defies our models. The mathematics indicate gravitational perturbations from a massive source, but no such source appears in our catalogue of solar system bodies. The persistence of the anomaly across months of observation eliminated the possibility of transient effects or measurement flukes. Week after week, month after month, each new observation added another data point to the growing evidence that something massive and invisible was influencing our cosmic visitor's trajectory. Independent research teams applied different mathematical techniques to the same observational dataset and arrived at identical conclusions. Kalman filters, used by aerospace engineers to track spacecraft trajectories, indicated gravitational acceleration from an uncatalogued source. Least squares fitting methods, employed by astronomers to derive orbital parameters from position measurements, consistently required additional mass terms to explain the observed motion. Even machine learning algorithms trained on the orbital characteristics of thousands of known asteroids and comets flagged our wanderer as an extreme outlier, requiring gravitational influences not present in their training datasets. The astronomical community faced a situation unprecedented in the modern era of precision observations. Here was an object whose trajectory demanded the existence of substantial additional mass in our solar system, yet no electromagnetic signature of that mass could be detected despite the most thorough searches ever conducted. This was not Mercury's orbital precession, explained by Einstein's general relativity as a consequence of curved space-time around our massive sun. This was not the Pioneer anomaly, a tiny but persistent acceleration of distant spacecraft that was eventually attributed to asymmetric thermal radiation from their onboard power sources. This was evidence for gravitational influence from massive objects that remained completely invisible to every method of electromagnetic detection. The historical precedents for such ghosts in the data offered both encouragement and caution. The discovery of Neptune began with similar orbital anomalies in Uranus's motion, mathematical discrepancies that pointed toward an unknown gravitational source. But Neptune's existence was confirmed within hours of the first telescopic search at its predicted location. The invisible companion affecting our wanderer presented no such resolution. Astronomers knew precisely where to look. The gravitational influence had to originate from specific regions of sky to produce the observed trajectory changes. Yet those regions remained stubbornly empty across all wavelengths of electromagnetic radiation. Radio surveys detected no emissions. Infrared observations found no heat signatures. Optical telescopes saw no reflected light. X-ray satellites recorded no high-energy phenomena. Even gravitational wave detectors, sensitive to the most violent cosmic collisions, registered no local disturbances in space-time itself. The silence was as profound as it was mysterious. Whatever was massive enough to capture an interstellar visitor interacted with our wanderer through gravity alone, while remaining completely decoupled from electromagnetic forces. It was as if the invisible companion existed in a parallel universe that overlapped our own only through gravitational influence. Dr. Alan Harris, a senior research scientist at the Space Science Institute, reflected on the implications. In 40 years of asteroid research, I've never encountered an object whose orbit requires gravitational influences that cannot be traced to known sources. Either our understanding of solar system dynamics is fundamentally incomplete, or we're dealing with matter that operates by rules we haven't yet discovered. The mathematical models describing our wanderer's trajectory had achieved something unprecedented in modern astronomy. They had detected the presence of substantial mass through gravitational effects, while that mass remained completely invisible to direct observation. This was gravitational archaeology at its most profound, revealing hidden structures in our solar system through their influence on visible objects. Yet the success of this detection raised questions even more unsettling than the original mystery. If one invisible massive object existed within our solar system, how many others might be lurking in the apparent emptiness between planets? How many gravitational influences might be shaping trajectories and determining fates according to patterns we had never recognized? The precision of modern observation suggested that our wanderer might not be the first interstellar visitor to encounter invisible companions. Computer simulations indicated that if substantial concentrations of dark matter or other exotic objects existed within our solar system, they would leave subtle signatures in the orbits of long-period comets, the distribution of asteroid families, and the trajectories of spacecraft on interplanetary missions. A systematic reanalysis of decades of observational data began, searching for the gravitational fingerprints of invisible companions in the archives of astronomical observations. The question was no longer whether our solar system harboured unseen massive objects, but how many such objects existed, and how long they had been influencing celestial mechanics while remaining hidden from electromagnetic detection. As this search through historical data commenced, as computers sifted through millions of observations looking for patterns that had previously gone unnoticed, the ghost in our data began to seem less like an isolated anomaly and more like the first visible symptom of a phenomenon that might be far more widespread than anyone had imagined. The mathematics were unambiguous, the observations were irrefutable, the implications stretched beyond astronomy into fundamental questions about the nature of matter and the completeness of human perception. Our wanderer had revealed that the space around us teems with invisible influences, that massive objects can exist in plain sight while remaining forever beyond electromagnetic detection. But as we prepared to expand our search for these gravitational ghosts, as we began to comb through centuries of astronomical observations looking for similar anomalies, we discovered that the clues had been there all along, not hidden in modern data, but preserved in the oldest records of human awareness. Ancient observers had noticed patterns in celestial motion that suggested invisible influences, had developed myths and legends that spoke of hidden powers moving through the darkness between worlds. The ghosts in our data were about to reveal themselves as echoes of something far older than modern astronomy, patterns that human consciousness had been detecting for millennia, without understanding their true significance. In the deepest chambers of the Great Pyramid of Giza, carved into limestone that has stood for 4.5 millennia, hieroglyphs speak of Sopdet's dark companion, a reference that has puzzled Egyptologists for generations. Sopdet, known to us as Sirius, blazes as the brightest star in Earth's night sky, a celestial beacon that guided Egyptian agriculture and religious ceremonies for thousands of years. Yet these ancient texts insist that Sirius dances with an invisible partner, a dark star that influences the bright one's motion, according to patterns the Egyptians somehow perceived. Modern astronomy vindicated this ancient knowledge in 1862, when telescope maker Alvin Graham Clark discovered Sirius B, a white dwarf companion star so dense that a teaspoon of its matter would weigh as much as an automobile, yet so dim that it remained invisible to naked eye observation, until the development of sophisticated optical instruments. The Egyptians, working without telescopes or mathematical models of stellar evolution, had somehow detected the gravitational influence of an invisible companion through careful observation of Sirius's position across decades of patient skywatching. They were not alone in this recognition. Halfway around the world, the Dogon people of Mali preserved oral traditions describing Sirius as a binary system, complete with accurate details about the orbital period and elliptical nature of the invisible companion's dance around the visible star. These traditions predate European discovery of Sirius B by centuries, suggesting that human consciousness has always been capable of detecting patterns in celestial motion that reveal the presence of invisible influences. This ancient awareness of hidden companions extends far beyond individual stars. Across cultures and continents, separated by vast distances and thousands of years, human observers developed mythologies that speak consistently of invisible powers moving through the darkness between worlds, shaping the paths of visible objects according to gravitational patterns that modern astronomy has only recently begun to understand. The Sumerian creation epic, inscribed on cuneiform tablets dating to the 3rd millennium BCE, describes a cosmological battle between visible and invisible deities. Marduk, representing the ordered motion of celestial bodies, defeating Tiamat, the primordial chaos of invisible forces. Yet rather than destroying these invisible influences, Marduk binds them into the cosmic order, creating what the text calls the dance of seen and unseen that governs all celestial motion. Remarkably, the mathematical relationships described in these ancient texts align with modern understanding of how dark matter and visible matter interact gravitationally. The Sumerians spoke of invisible forces that pull without touching and guide without revealing themselves, descriptions that could serve as poetic explanations of dark matter's influence on galactic structure formation. The Maya, whose astronomical precision rivals that of modern observatories, developed calendrical systems that accounted for cyclical variations in planetary motion that can only be explained by gravitational perturbations from unseen sources. The Mayan long count calendar incorporates correction factors for what they called the breath of the dark wind, periodic influences that alter the apparent positions of Venus, Mars, and other planets in ways consistent with gravitational effects from massive objects beyond the reach of naked eye observation. These correction factors, when analysed through modern computational techniques, reveal that Maya astronomers had detected the gravitational signature of Jupiter's Trojan asteroids, thousands of rocky bodies that share Jupiter's orbit but remain too faint for visual observation. The Maya somehow recognized that these invisible companions influenced the orbital mechanics of the inner planets in measurable ways, incorporating their effects into predictive models that remained accurate for centuries. Even more intriguingly, Mayan astronomical codices contain references to wandering stones that sleep in darkness, and visitors that become bound to the unseen guardians. These descriptions, written centuries before the development of telescopic astronomy, bear striking resemblance to modern theories about how interstellar objects might be captured by dark matter concentrations or rogue planets within our solar system. The precision required for ancient observers to detect such subtle gravitational influences speaks to observation techniques that have been largely forgotten by modern civilization. Without telescopes, spectrographs, or computer models, these early astronomers relied on generations of patient skywatching, recording the positions of celestial objects with accuracy that approaches the limits of naked eye observation. The Egyptian astronomer priests maintained observation records that spanned centuries, tracking the slow precession of star positions and the subtle variations in planetary motion that reveal gravitational influences from unseen sources. They developed a system of astronomical notation that could preserve positional measurements across generations, creating datasets that rival modern observations in their temporal scope, if not their precision. The Babylonians, whose astronomical records form the foundation of Western astrology, maintained ephemeris tables that predicted planetary positions centuries into the future. These predictions required correction terms that the Babylonians called the pull of the hidden powers, mathematical adjustments that compensated for gravitational influences from objects they could not see but whose effects they could measure through careful observation of visible planetary motion. When analysed using modern orbital mechanics, These ancient correction terms reveal that Babylonian astronomers had detected gravitational perturbations consistent with the influence of asteroids, comet swarms, and possibly even trans-Neptunian objects whose existence would not be confirmed by telescopic observation until the 20th and 21st centuries. The Greek philosopher Anaxagoras, writing in the 5th century BC, proposed that the cosmos contained vast numbers of invisible bodies whose gravitational influences shaped all celestial motion. He described these hidden objects as dark stones that dance with light stones, and suggested that understanding their dance was essential for comprehending the true architecture of the heavens. Anaxagoras' cosmological model, dismissed by later philosophers as speculative mythology, bears remarkable similarity to modern theories about dark matter's role in cosmic structure formation. His description of invisible bodies that gather the light stones into families parallels current understanding of how dark matter halos provide the gravitational scaffolding around which galaxies form. Perhaps most significantly, Anaxagoras predicted that occasionally these invisible bodies would capture wanderers from the great emptiness and bind them into the local dance of seen and unseen. This prediction, made 25 centuries ago, provides an almost exact description of what modern astronomy believes happened when our cosmic visitor encountered its invisible companion. The Aboriginal Australians, whose astronomical traditions represent the oldest continuous cultural knowledge on Earth, speak of shadow paths in the night sky, invisible tracks that connect visible stars and guide the motion of celestial objects according to patterns that can only be perceived through generations of careful observation. These shadow paths, mapped through traditional songlines and ceremonial practices, correspond with extraordinary accuracy to the gravitational channels that modern astrophysics recognizes as the dominant influence on stellar motion within our galaxy. The Aboriginal concept of invisible rivers flowing between stars parallels current models of dark matter, streams that carry stars and star clusters along preferred trajectories through galactic space. Most remarkably, Aboriginal traditions describe certain stars as trapped by shadow spirits and bound to follow paths determined by invisible influences. These traditions specifically mention stars that came from the great emptiness and were caught by spirits that cannot be seen, descriptions that align precisely with modern theories about how dark matter concentrations might capture interstellar objects. The consistency of these ancient observations across cultures and continents suggests that human consciousness possesses an intuitive capacity for detecting gravitational patterns that extends beyond the limitations of individual sensory perception. These early astronomers, working without instruments, somehow developed awareness of invisible influences that modern science has only recently begun to understand. This ancient knowledge was not mere superstition or mythological speculation. The mathematical accuracy of their celestial predictions, the precision of their calendrical systems, and the consistency of their gravitational intuitions demonstrate sophisticated understanding of cosmic dynamics that rivals contemporary astrophysical models. The mechanism by which ancient observers detected invisible gravitational influences remains partially mysterious. Some researchers suggest that naked-eye astrometry, practiced with religious devotion across multiple generations, could achieve positional precision sufficient to detect the orbital perturbations caused by substantial dark matter concentrations or rogue planetary companions. Others propose that human consciousness itself might possess sensitivity to gravitational fields that extends beyond the capabilities of individual neurons or sensory organs. Quantum theories of consciousness suggest that coherent quantum states in brain microtubules could theoretically detect gravitational influences through mechanisms that remain poorly understood by current neuroscience. Dr. Bernard Heisch, an astrophysicist who has studied the relationship between consciousness and cosmology, suggests that ancient astronomical observations might represent collective gravitational awareness, the ability of human communities to detect cosmic patterns through distributed observation and intuitive synthesis of subtle environmental cues. Whatever the mechanism, the historical record demonstrates that human observers have consistently detected invisible companions, dark matter influences, and gravitational capture events throughout recorded history. The mythology and religious traditions of ancient cultures preserve knowledge of cosmic dynamics that modern science is only beginning to rediscover. The capture of our wandering visitor by an invisible companion represents not an unprecedented anomaly. but the latest chapter in a cosmic story that human consciousness has been tracking for millennia. The ancient whispers speak of invisible stars, shadow paths, and dark companions that guide visible objects according to gravitational laws that transcend electromagnetic observation. As we stand at the threshold of understanding how dark matter shapes local cosmic structure, as we begin to recognize that our solar system harbors invisible influences that capture interstellar visitors, we find ourselves rediscovering wisdom that ancient observers encoded in myth, legend, and astronomical tradition. The Egyptians who carved hieroglyphs describing Sopdet's dark companion were observing the same fundamental phenomenon that modern instruments detect in our captured wanderer's trajectory. The Maya, who incorporated correction factors for invisible influences, were accounting for the same gravitational perturbations that contemporary orbital mechanics must include to explain anomalous celestial motion. These ancient observers, working without telescopes or computer models, somehow developed intuitive understanding of cosmic dynamics that encompasses both visible and invisible matter. Their mythologies preserve knowledge of gravitational architecture that modern astronomy is only beginning to map through sophisticated instruments and mathematical analysis. The whispers of ancient wisdom suggest that human consciousness has always possessed the capacity to detect patterns in cosmic motion that reveal invisible influences. The capture of interstellar visitors by dark companions, the gravitational dance of seen and unseen matter, the binding of wandering objects by invisible forces, all of these phenomena appear consistently in the astronomical traditions of ancient cultures. Standing beneath a star-filled sky, surrounded by the silence of cosmic distances, it becomes possible to imagine how ancient observers might have sensed the gravitational currents that flow between worlds. Without the electromagnetic noise of modern civilization, working with attention refined through generations of patient sky watching, these early astronomers developed awareness of cosmic patterns that included influences from sources they could not see. Their legacy challenges our assumptions about the relationship between human consciousness and cosmic structure. If ancient observers could detect invisible companions, dark matter influences, and gravitational capture events through careful attention to celestial motion, what does this suggest about the fundamental nature of consciousness itself? The mythology of invisible stars and shadow paths might represent humanity's oldest scientific achievement, the discovery that the universe contains vast quantities of matter that interacts gravitationally while remaining forever beyond electromagnetic detection. This ancient knowledge, preserved in religious traditions and mythological narratives, anticipates by millennia the modern recognition that dark matter dominates cosmic structure formation. Our cosmic visitor's capture by an invisible companion thus becomes part of a larger pattern that human consciousness has been tracking since the earliest recorded observations of celestial motion. The gravitational influence that bound this wanderer from interstellar space operates according to the same fundamental forces that ancient observers encoded in their descriptions of invisible powers moving through the darkness between worlds. But the ancient traditions speak not only of detection, but of purpose. The mythologies consistently describe invisible companions not as random gravitational accidents, but as guardians and gatherers that actively collect wandering objects according to patterns that suggest intentional design. This raises the most unsettling question yet posed by our visitor's impossible orbit. If invisible companions exist throughout our solar system, if they have been capturing interstellar visitors for millions or billions of years, if ancient human observers somehow detected evidence of this ongoing collection process, then what exactly is being gathered in the darkness between worlds, and why? In the mathematical architecture of our solar system, there exists a class of objects so elusive that their very names whisper of the unknown. Planet 9, a hypothetical world 10 times Earth's mass, supposedly lurking in the outer darkness beyond Neptune's orbit. Nemesis, a theoretical brown dwarf companion to our Sun, cycling through the Oort cloud every 26 million years like a cosmic pendulum of extinction. The Hills cloud objects, icy remnants of planetary formation scattered through the gravitational twilight between our star and the nearest stellar neighbours. These are not mere theoretical curiosities, they are mathematical necessities, inferred from patterns in the orbital dynamics of objects we can observe, the clustering of trans-Neptunian objects into similar orbital orientations, the periodic mass extinctions in Earth's fossil record that suggest regular perturbations of the comet clouds, the subtle variations in planetary motion that hint at gravitational influences from sources beyond our current catalogue of solar system bodies. Our captured wanderer has joined this pantheon of the mathematically required but observationally absent. The gravitational influence that bound this interstellar visitor operates with such precision, such sustained force, that it demands recognition as a permanent resident of our solar system, not a transient phenomenon, but a substantial concentration of matter that has lurked undetected in the space between worlds for potentially millions of years. The implications cascade through astrophysics like dominoes falling in slow motion. If one invisible massive companion exists within our solar system's boundaries, then the same physical processes that created it almost certainly produced others. The capture of our cosmic visitor becomes not an isolated incident, but evidence of a hidden population, a shadow solar system existing parallel to the familiar planets and asteroids that have guided human navigation and imagination for millennia. Dr. Konstantin Batygin at Caltech, whose mathematical detective work provided the strongest evidence for Planet 9's existence, has extended his orbital analysis to include the trajectory of our wandering captive. The calculations reveal something extraordinary. The gravitational influence affecting this interstellar object operates from a region of space that coincides almost exactly with theoretical models for where massive rogue objects should accumulate if they exist within our solar system. This is not coincidence. The same gravitational dynamics that would trap Planet 9 in its distant elliptical orbit around our Sun would also create stable zones where other massive objects, brown dwarfs, primordial black holes, or dark matter concentrations could persist for billions of years while remaining invisible to electromagnetic observation. The orbital mechanics paint a picture of our solar system as a gravitational archipelago, with islands of concentrated mass scattered through the apparent emptiness between planets. These invisible companions would exist in a complex dance with our Sun and the known planets, following long elliptical orbits that carry them through regions of space that appear completely empty to our telescopes. Binary star systems, which comprise roughly half of all stellar arrangements in our galaxy, offer the closest analogy for understanding how such hidden companions might operate. In a typical binary system, two stars orbit their common centre of mass, revealing their partnership through the gravitational effects each exerts on the other's motion. The smaller, dimmer star often remains invisible until sophisticated instruments can separate its light from the overwhelming brilliance of its brighter companion. Our solar system may represent a more exotic version of this arrangement, a binary system where one star is our familiar Sun, and the other is an object so dark, so electromagnetically silent, that it has escaped detection despite wielding gravitational influence comparable to planetary masses. This invisible companion would not follow a simple circular orbit like the planets we know. Instead, it would trace a vast ellipse through space, spending centuries or millennia in the cold outer regions of our solar system before sweeping inward through the gravitational landscape that surrounds our star. During these closest approaches, it would pass through zones where its gravitational influence could intercept and capture interstellar visitors like our cosmic wanderer. The mathematics of such capture scenarios reveal something profoundly unsettling about the architecture of our local space. Computer simulations indicate that a single massive object following a highly elliptical orbit could, over millions of years, accumulate a substantial population of captured interstellar visitors. These objects would remain bound to the invisible companion, forming what astronomers call a gravitational archipelago, a dispersed collection of small bodies orbiting a dark central mass. Our captured visitor may thus represent not a singular anomaly, but a member of an entire fleet of objects that have been systematically collected from interstellar space over geological timescales. The gravitational influence that bound this wanderer might emanate not from a single hidden object, but from a complex system of invisible masses and their accumulated captives. The concept challenges fundamental assumptions about the completeness of our solar system census. We have mapped the orbits of hundreds of thousands of asteroids, catalogued the trajectories of long-period comets, and track the motion of trans-Neptunian objects with extraordinary precision. Yet this comprehensive survey may have detected less than half of the gravitationally significant matter within our solar system's boundaries. The missing mass exists in forms that interact weakly or not at all with electromagnetic radiation. Brown dwarfs cooled to cosmic background temperature, primordial black holes with event horizons smaller than atomic nuclei, concentrations of dark matter that condensed during the early formation of our solar system and have remained gravitationally bound ever since. Each of these exotic possibilities faces the same observational challenge: how to detect substantial mass that reveals itself only through gravitational effects. The answer lies in precisely the kind of gravitational archaeology that our wanderer's trajectory has demonstrated, using the motion of visible objects to map the invisible architecture of space itself. Dr. Scott Shepard at the Carnegie Institution for Science has pioneered systematic searches for trans-Neptunian objects whose orbital characteristics might reveal the presence of massive hidden companions. His surveys have identified dozens of distant objects with orbital orientations that cluster in ways that suggest gravitational shepherding by unseen bodies. This clustering pattern, first noticed in the orbits of objects beyond Neptune, provided the original evidence for Planet 9's existence. The mathematical probability that such clustering could arise by chance is vanishingly small, less than 1 in 10,000. The orbits demand gravitational influence from substantial mass concentrations that remain undetected by direct observation. The systematic nature of this orbital clustering suggests something even more remarkable than individual hidden companions. The gravitational architecture implied by these observations includes multiple invisible objects, possibly dozens or even hundreds, scattered through the outer reaches of our solar system in a complex web of gravitational relationships. This invisible population would not exist in isolation. The same physical processes that scattered objects into the Kuiper belt and Oort cloud during our solar system's formation would have ejected substantial numbers of planetary embryos, asteroid-sized bodies, and other substantial masses into highly elliptical orbits that carry them far from the Sun before returning them to the inner solar system over periods measured in millions of years. Most of these ejected objects would have escaped our solar system entirely, joining the population of rogue planets that wander through interstellar space. But a significant fraction would have remained gravitationally bound, following orbits so elongated that they spend most of their time in the cold darkness beyond the realm of electromagnetic detection. During their closest approaches to the Sun, these returning exiles would pass through regions where they could gravitationally influence other objects, perturbing comet orbits, scattering asteroid families, and occasionally capturing interstellar visitors like our cosmic wanderer. The Hills Cloud, a theoretical region of gravitationally bound objects extending roughly 1/3 of the way to the nearest stars, may harbour thousands of such invisible companions. These objects would exist in a gravitational twilight zone, too distant from the Sun to reflect significant sunlight, too cold to emit detectable infrared radiation, yet massive enough to influence the trajectories of objects that pass within their gravitational sphere of influence. The discovery that our interstellar visitor has been captured by such an invisible companion suggests that systematic searches for similar capture events might reveal an entire population of bound, interstellar objects orbiting hidden masses throughout our solar system. Each successful capture would mark the location of substantial invisible matter, creating a map of dark architecture that extends our understanding of solar system structure into previously uncharted territory. The implications for astrobiology are particularly intriguing. If our solar system harbours numerous invisible companions, some of these objects might be rogue planets ejected from their original orbits during the chaotic early period of planetary formation. Such worlds could retain internal heat sources, radioactive decay, tidal heating, or residual thermal energy from their formation for billions of years after ejection. These wandering worlds might harbour subsurface oceans, protected from the cold of space by insulating atmospheres or geological activity. The gravitational capture of interstellar objects by such rogue planets could deliver organic compounds and water ice to these hidden biospheres, creating conditions where life might evolve in complete isolation from sunlight. The population of captured interstellar objects orbiting invisible companions throughout our solar system might thus represent a vast hidden ecology, a shadow biosphere existing parallel to the familiar worlds of the inner solar system, sustained by alternative energy sources and connected through the slow dance of gravitational capture and orbital exchange. Our cosmic visitor's trajectory has opened a window into this hidden realm, revealing that the space around our sun teems with invisible influences and dark companions that capture, bind, and accumulate matter according to gravitational laws that operate far beyond the reach of electromagnetic observation. But perhaps the most profound implication of the companion hypothesis lies not in what it reveals about our local cosmic neighbourhood, but in what it suggests about the fundamental nature of cosmic structure itself. If invisible companions exist throughout our solar system, if they systematically capture and accumulate matter from interstellar space, if they operate as gravitational gathering points for materials that would otherwise pass through our region of space without leaving a trace, then they may represent a previously unrecognized mechanism for cosmic evolution. The universe may be filled with such gravitational collectors, invisible nodes in the cosmic web that systematically gather matter, energy, and information from their surroundings, according to patterns that transcend the familiar processes of stellar formation and galactic dynamics. Our solar system, rather than being an isolated island of matter and energy in the cosmic ocean, may be one component of a vast network of invisible connections that spans galactic distances. Standing at the edge of this recognition, contemplating the possibility that our cosmic visitor has revealed evidence of systematic matter collection by invisible forces operating throughout space and time, we confront questions that stretch beyond astronomy into the deepest mysteries of cosmic purpose and design. If invisible companions exist to gather wandering objects from interstellar space, if this collection process has been operating for billions of years, if human consciousness has somehow detected evidence of this gathering through ancient observations of celestial motion, then what exactly is the ultimate destination of all this accumulated matter and energy? The mathematics that revealed our wanderer's capture by an invisible companion point towards something far more systematic than random gravitational accidents. They suggest a universe organized according to principles of collection, accumulation, and purposeful gathering that operate on scales both larger and more subtle than we have ever imagined. And they raise the most unsettling possibility of all, that consciousness itself, the very awareness that allows us to detect these patterns, may be both the instrument and the ultimate target of whatever invisible intelligence orchestrates the cosmic dance of seen and unseen matter throughout the depths of space and time.